Hi, tonight we'll be talking about chemical bonding and the Lewis model in chapter 9. And we want to ask ourselves, why do atoms bond? So chemical bonds form because of the lower potential energy. So lower potential energy between the charged particles that compose atoms. A chemical bond forms when the potential energy is less than the potential energy of the separate atoms. So to calculate this potential energy, we want to look at the nucleus-to-nucleus repulsions, electron-to-electron repulsions, and nucleus-to-electron attractions. We can look at the different types of bonds, the metal and non-metal, which forms an ionic bond, and we learned that electrons are transferred. For non-metal and non-metal, we have covalent bonding, and electrons are shared. However, when we have metal and metal bond, it's a metallic bond, and the electrons are pooled together. And here are some examples. Take, for example, sodium and chloride. You form table salt. Sodium chloride, a metal and non-metal, transfer of electrons. Sodium transfers an electron to chlorine, and chlorine becomes a chloride, and we have sodium plus, so sodium chloride. We have covalent bonding, the sharing of electrons between two H atoms and one oxygen atom to form H2O, water molecules. Or we can also look at sodium metal itself that forms metallic bonds, and we have a sea of electrons going around the Na plus ion. So we can say that when a metal atom loses an electron, it becomes a cation, and when a nonmetal gains an electron, it becomes an anion. The oppositely charged ions therefore form an ionic bond. Covalent bonds involve the sharing of electrons, and you have nonmetal atoms with very high energies to ionize them. So when they bond together, it is better to share valence electrons, so the potential energy will be really, really low. So shared electrons hold the atoms together. Metallic bonds, however, have very, very low ionization energies, and electrons are easily lost. So a simple theory involves metals releasing their valence electrons and shared by a pool of cations. So the metal cation is an island with a sea of electrons being delocalized throughout the metal structure. And as you can see, here are the sodium plus cations, and with a sea of electrons traversing around the crystal lattice. So when we refer to valence electrons, they're the electrons in the outermost shell and are held most loosely. Chemical bonding involves the transfer for ionic or sharing for covalent of electrons between two or more atoms. Lewis theory focuses on the behavior of the valence electrons. So we want to talk about Lewis theory of bonding. So first we want to determine the number of valence electrons in an atom. So the column number in the periodic table will tell us how many valence electrons a main group atom has. If we take a look at oxygen, in a Lewis structure, we represent the valence electrons as dots. So oxygen has 6, 2, 4, 6 electrons surrounding the symbol O for oxygen, and we refer to this as the Lewis electron dot structure. And so for lithium in group 1, and then sodium could also have 1 dot, potassium could have 1 dot, but then when we go to group 2, we see beryllium with 2, because it's in group 2, so it has 2 dots to represent the s orbital electrons. For boron, B, when we go to, has 3 dots, and for carbon, C, 4 dots. For nitrogen, 5, oxygen, 6, fluorine, 7, and of course neon would have 8. So we like to talk about the stable electron arrangements, and K plus has an octet. That means it's more stable when it is in this arrangement as opposed to the potassium ion where you have 4s1. Metals form cations by losing valence electrons, and nonmetals gain them by gaining electrons, and you form an octet. So Lewis bonding theory states that atoms bond because it results in a more stable electron configuration, lower potential energy. And these results return out, an outer shell ends up with 8 electrons. And the key to try to remember this is like the metal and non-metal want to obtain the electron configuration of noble gases. The Tech rule therefore states when atoms bond, they tend to gain or lose or share electrons so that they might have 8 valence electrons. So our noble gas configuration, if we start with neon, is NS2, NP6. And there are of course many exceptions, hydrogen, lithium, beryllium, and boron, because helium only has 2 valence electrons. We have lithium loses 1, hydrogen gains or shares 1 electron, and so there are exceptions to the rule. Those are some exceptions, but then we can also have what's referred to as an expanded octet using the empty valence d orbitals that we learned a while back. So Lewis theory again, if we had potassium in group 1, potassium metal plus chlorine that has 7 valence electrons, potassium will lose an electron to chlorine and ends up with a plus charge and becomes a potassium cation, while chlorine gains an electron and becomes a chloride anion. And Lewis theory predicts this correctly and allows us to predict the relative strengths of the ionic bonds based on Coulomb's law. So when we look at the energy involved in ion bond formation when sodium is ionized to the gaseous state and loses an electron, it takes around 496 kilojoules per mole to release that electron. Whereas chlorine gas itself loves to accept an electron, and so the energy involved would be minus 244 kilojoules per mole, and so hence most organic compounds have a really large energy that's released, and that's why it's a negative minus 411 kilojoules per mole. So the heat of formation for most ionic compounds is exothermic. That means it gives off or releases heat and is very large. So we call the structure in a metal a crystal lattice. This is held together by just the electrostatic attraction of cations around the sea of electrons. And so if we look at the crystal lattice, there is no direct cation-anion pair because you have the cations, but then the electrons are going around as a sea of electrons. But when you have sodium chloride, on the other hand, like in this picture then, you have sodium, the purple, and the green are the chloride ions, so sodium chloride forming a cubic lattice. So the extra stability can be measured in the form of lattice energy, and it's always exothermic, and it depends directly on the size of the charges and inversely proportional on the distance between the ions. So how do we determine the lattice energy? Born and Haber came up with a hypothetical series of reactions that came up with the crystal lattice energy for sodium chloride. For all intents and purposes, you will not be quizzed on this, but it's nice to take a quick look at the cycle as we form the table salt, sodium chloride. So we start out first by ionizing sodium and chlorine and to form table salt, and because it gives off a lot of energy and the product, sodium chloride, has a lower potential energy than the metal and non-metal, and so its table salt is formed. So what's the trend in lattice energy? The larger the ion, the weaker attraction. And so if it's a weaker attraction, so smaller lattice energy. So as we go down, as the ion size gets larger, so you have potassium, rubidium, cesium, and francium, they end up with smaller lattice energies because they are much smaller, and this is evidenced by the lattice energy in kilojoules per mole. So lithium is minus 834, while as we go down, a weaker attraction, minus 657. So what are the trends? So the force of attraction between oppositely charged particles is directly proportional to the product of the charge. So the larger the charge, stronger attraction, larger lattice energy. So ion charge is normally quite important. So when we go to the bonding versus what is actually real, then the Lewis theory implies that attractions between ions are strong. Lewis theory predicts ionic compounds should have high melting points. And sure enough, the melting point of sodium chloride is normally in much greater than 300 degrees C, I think about 900 or so. What are the properties of ionic compounds? They are hard and brittle. If you take table salt and try to feel, you can in fact feel the cube, and they are solids at room temperature, very high melting points, and of course they are quite soluble in water. So sodium chloride, as we heat them, you end up dissolving the ions that are in the crystal. So ionic bonding versus reality. Most ionic solids are relatively hard. Lewis theory predicts that moving ions out of position will be quite difficult, and the harder the material that one cuts, it doesn't streak. So Lewis theory also implies that when ions are displaced from their position in their crystal lattice, repulsive forces occur. So ionic solids are brittle, and when we hit them, they're brittle, so they shatter. To conduct electricity, though, a material must have a charged particle, a plus or a minus, and Lewis theory implies that the ions are in locked position and cannot move. Ionic solids do not conduct electricity. Sodium chloride solid will not conduct electricity, but when we dissolve it in water, then the ions will have the ability to move around, and therefore it will conduct electricity. So we can do this in the lab by checking out whether table solid will conduct electricity, and of course it doesn't. But then when you add water, then the light bulb turns on, allowing the ions to separate and the charges to move. Now let's go to Lewis theory of covalent bonding. This theory implies that another way atoms can achieve an octet is by sharing their valence electrons. And we refer to that as covalent bonding. Electrons that are shared are called bonding pairs, but then electrons that are not shared are referred to as lone pairs. So when we look at water, there are two electrons that are being shared by hydrogen and oxygen. And in this hydrogen that contributes an electron, it's also sharing another electron from hydrogen, but there are two pairs or four electrons that are non-bonding pairs. So when we say non-bonding pairs, there are two sets of non-bonding pairs. When two atoms share a pair of electrons, we call that a single covalent bond. But when they use more than one single bond, then it fills an octet. So here's the octet, 2, 4, 6, 8, and if there's 2, a duet, if 3, a triplet. And when we look at oxygen, right, so O2, oxygen exists naturally as a diatomic molecule, so we have O2. So O has 6 electrons, 2, 4, 6. So O plus O gives us an octet this way, and we represent the bonding pairs with 2 straight lines. So oxygen has 2 bonding pairs and 1, 2, 3, 4 non-bonding pairs. A triple or covalent bond consists of 6 electrons, as in the case of nitrogen. So if we have nitrogen has 5 electrons, there are 1, 2, 3, 4, 5, and so they share, these 2 nitrogen atoms share to form the N2 nitrogen molecule. So what does the model tell us versus reality? That oxygen generally forms 2 single bonds or a double bond with other compounds. Hydrogen and halogens tend to form molecular elements. And we can in fact predict their molecular formulas with the Lewis theory when we try to figure out what is more stable: oxygen when it is singly bonded to 2 other atoms, or when it is in the form of hydrogen peroxide, H2O2. What does the model tell us with covalent bonding versus reality? That compounds of nonmetals are made of individual molecule units. So molecular compounds have very low melting points and boiling points. So then they would be less than and all are found in 3 states at room temperature. For example, we have water. This happens to be C5H12, so this happens to be pentane. Strong covalent bonds within the molecules, but then weaker intermolecular forces between molecules. We have a molecular compound and an organic compound, C5H12. And then when we look at the hardness and brittleness of molecular compounds, some like ice could be solids and brittle, but some could be soft and waxy. Molecular compounds do not conduct electricity because there are no ions, cations or anions, but molecular acids can conduct electricity when we dissolve it in water. Bond strength is also measured by how much energy must be added into the bond to break it. So triple bonds are much stronger than double bonds, and double bonds are much stronger than single bonds. Bond length is also determined by measuring the distance between the nucleus of bonded atoms. So if we have triple bonds, they are shorter than double bonds, which are also much shorter than the single bonds. So single bonds are by far the longer bond. Polar covalent comes about when an atom pulls electrons more closer to its nucleus. And as a result, we end up with what is referred to as a polar bond. And when we look at hydrofluoric acid, we know that the fluoride tends to draw the electrons much more closer to it than hydrogen, so we tend to draw the dipole with the arrow pointing to the more electronegative fluorine atom, and we designate a delta plus, the dipole, for on the side where hydrogen is would be slightly positive and where fluorine is slightly negative. So bond polarity is classified as an unequal sharing of enough to produce a dipole in the bond, and the degree of some sharing could lead to some ion formation. So then we come up with a new word called electronegativity. Electronegativity is the ability of an atom to attract bonding electrons. So electronegativity increases from left to right and increases across the period, and then as you go down the group from top to bottom. Fluorine is the most electronegative element, and francium is the least electronegative. Noble gas atoms are not assigned any values. So when we take a look at the electronegativity scale, if the difference in electronegativity between the atoms is 0, it would be a purely covalent, equal sharing. But if the difference is between 0.1 and 0.4, then it's a non-polar covalent. So we'll want to take note of polar non-polar covalent 0.1 to 0.4 if the difference, and polar covalent 0.5 to 1.9. So if the difference is around 2, right, then therefore it's 100% ionic. So as we see here, when electrons are shared equally, nonpolar covalent bond. Unequal sharing, a polar covalent bond, and then more than 2 electrons are transferred, the delta N, the electronegativity is greater than 2, then it's an ionic bond. The bond polarity for the effect of electronegativity on bond type. So it's a small, so here it is again summarized for you in a tabular form. When it's small, you end up with a covalent, nonpolar. But if you have 0.4 to 2, you have HCl. The chlorine atom draws the electrons much more than hydrogen. So therefore, it's an intermediate polar covalent bond, and when you have a really large difference, like table salt, then you have an ionic bond. So percent ionic character is a percent of a bond's dipole moment compared to what it would be if it was completely transferred. Lewis structures of molecules. Lewis theory, therefore, allows us to predict the valence electrons on molecules. And as a result of that, we can predict the shape of molecules. And because of the shape, then we can predict the properties of the molecules and how they will interact together. But we have to be careful because Lewis theory predicts that atoms will be most stable when their octet or when their octet of valence electrons is fulfilled. So it doesn't require that atoms have the same number of lone pair. We just first have to start with the octet rule. And there, of course, are some exceptions, and we'll work on some exceptions for the expanded octet. That means more than 8 valence electrons. So generally, this is how it follows. Carbon tends to have, because it has 4 Lewis dots, so we'll tend to have 4 bonds. Nitrogen will tend to have 3 bonds and 1 lone pair. Oxygen 2 bonds and 2 lone pairs, while hydrogen and halogen would have 1 bond. We'll work on that. Then we come to the concept of assigning formal charges. So for SO2, sulfur dioxide, how do we go about assigning formal charges? During bonding, atoms would end up with fewer or less electrons. So if we look at sulfur is underneath oxygen, right? So therefore it will have 6 electrons, valence electrons. And then because how many non-bonding? There are 2. And so the formula for the calculating formal charge is valence electrons minus non-bonding electrons minus half of the bonding electrons. So for sulfur, it would be +1, and for oxygen, 6 minus 6 plus 1/2 times 2 would be -1. So then SO2 doesn't have a charge. So the molecule would have a charge of 0. So there are some exceptions to the octet rule. For example, odd number electron species like NO will have 1 unpaired electron. Very, very reactive, of course. Or if we have incomplete octets like boron, because it has three electrons, and as well as aluminum. So when we come to the topic of resonance, resonance refers to the fact that when the electrons are delocalized to help stabilize the charge of the molecule, we can form more than one type of structure. So we call those resonance structures. but the actual molecule is actually a hybrid of the two. So if we look at SO2, we can put the lone pair here or here. And of course ozone, right? O3. So our ozone layer, and we will try to make an analogy of a hybrid dog, so that we can best picture how ozone is the resonance structure of ozone could either be this one on the left with the lone pairs on this oxygen, or you could have the lone pair electrons on this other oxygen on the other side, and the double bond would be where you just have 2,4, because as you look, right, it satisfies the Lewis theory, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, right? So that should help us visualize resonance structures. Only electron positions can change, and the structures must always have the same number of electrons. And then the second row can have a maximum of 8 bonding and non-bonding, while the third row will have an expanded octet. For example, if we want to draw the resonance structures for nitrate and O3, first we want to assign formal charges and try to move the electron pairs so that from the atoms with negative formal charges toward the atoms with a more positive forward charge. So in other words, this is more negative, so we'll want to move the electrons, so then we'll end up with 2 bonds, and then we'll move this pair of electrons over here, so then it would have a negative charge. So this becomes negative, and this becomes negative, while this becomes, this now has no charge, right? Well, nitrogen is still slightly positive. So when we look at sulfuric acid, H2SO4, so we write down, draw and sketch sulfuric S, and then write down the 4 O's, and then attach an H. So in fact we can draw, so if we have the O's here, if we put the dots in the O's opposite each other, we can actually move this electron to this side, so then you have two bonds, and then you can move this lone pair so that then they would share, sulfur and oxygen would be sharing another pair of electrons, and you would have this other resonance structure. So how do we evaluate resonance structures? We have to make sure that they have fewer formal charges and they are much smaller, and that the better structures will have the negative formal charge on the more electronegative atom. When we come to bond energies, chemical reactions involves breaking and forming bonds. So the heat of their reaction can be compared by breaking old bonds and making new bonds. We refer to this as the bond energy. And the trend tends to be, for a triple bond, 837 kilojoules, which is greater than the carbon double bond, which is 611 kilojoules, and which is greater than carbon-carbon single bond, which is only 347 kilojoules. Likewise, if you have carbon-nitrogen double bond, carbon-nitrogen single bond. So the shorter the covalent bond, the stronger it is. So the triple bonds are much, much stronger as shown in their bond energies. But when we compare similar types of bonds get weaker down the column and get stronger across a period. So if we have Br and F, right, 237 kilojoules, but when we just have Br and Cl, it's 218 kilojoules. Well, we have Br and Br, 193 kilojoules. So we can, in fact, estimate the heat of the reaction by summing together the bonds broken and the bonds formed, and we refer to that as the enthalpy change of the reaction from bond energies. This is more a concept in 1046, so you will not be quizzed too much on that. But we just want to realize that the trends in bond energies, triple bonds are much stronger than double bonds, which are much stronger than single bonds, and then we need to know the trends that the bonds get weaker as we go down the column. So the bond lengths are as such that the trends in bond lengths are similar also. The carbon-carbon triple bond is much shorter, so it's 120 picometers, while just a single carbon-carbon bond is 154 picometers. So also, the bond length decreases from left to right, so carbon-carbon. So from left to right, the bond decreases, so carbon-oxygen bond would be much shorter, 143 picometers as opposed to 154 for carbon-carbon. And then the bond length also increases down the column, so we have Br-Br, bromine-bromine, 228. So as the bonds get longer, they get weaker, so that's what you will want to know. Metallic bonds, though, have very, very low ionization energies, as we discussed, right? We have a sea of electrons along the metal crystal lattice. And so what does it tell us in reality? That sodium metal, metallic solids, conduct electricity really, really well. And heating will cause metal atoms to vibrate faster, and therefore will make it more difficult for electrons to travel through a crystal. So as the temperature increases, the conductivity of the metal will decrease. Metallic bonding versus reality. Heat is a form of motion, kinetic energy. So collisions, therefore, transfer energy from one atom to the next. So metallic solids, therefore, sodium, aluminum, do conduct heat well. And then metallic bonding, also atoms emit light when electrons jump from higher energy to lower energy level. So metallic solids do reflect light. According to the metallic bonding theory, attractive forces that hold the structure together result from the attraction of metal atom cores. So, therefore, it will not break, but it is malleable and ductile, so we can pound and form it into any shape we like. So, at the core of the atoms, the delocalized electrons is strong because it has full charges. But if we want to heat it in order to boil, all the attractions must be broken. So when we melt, all the attractions are broken. And then, therefore, since the metals should really have really high boiling points. So most metals have higher boiling points with the exception of mercury, which is a solid at room temperature. So when we look at metals, they tend to have melting points that increase from left to right across the period. So Aluminum has a higher melting point than magnesium and a higher melting point than sodium. And also melting points decrease as we go down the column. So if you look at lithium, sodium, and potassium, that in fact lithium has 180 while potassium only has 63. And so that concludes our chapter 9 lecture on Lewis bonding, one form of chemical bonding.